Dear students, do you want to get into the fascinating world of physics? Please see this video and also subscribe to this channel.
1.3 Conductors and insulators. Some substances readily allow passage of electricity through them, others do not. Those which allow electricity to pass through them easily are called conductors. They have electric charges, electrons, that are comparatively free to move inside the material. Metals, human and animal bodies and earth are conductors. Most of the non-metals like glass, porcelain, plastic, nylon, wood offer high resistance to the passage of electricity through them. They are called insulators. Most substances fall into one of the two classes stated above. When some charge is transferred to a conductor, it readily gets distributed over the entire surface of the conductor. In contrast, if some charge is put on an insulator, it stays at the same place. You will learn why this happens in the next chapter. This property of the materials tells you why a nylon or plastic comb gets electrified on combing dry hair or on rubbing, but a metal article *. There is a third category called semiconductors, which offer resistance to the movement of charges, which is intermediate between the conductors and insulators. 4. Physics like spoon does not. The charges on metal leak through our body to the ground as both are conductors of electricity. However, if a metal rod with a wooden or plastic handle is rubbed without touching its metal part, it shows signs of charging. 1.4 Basic properties of electric charge. We have seen that there are two types of charges, namely positive and negative, and their effects tend to cancel each other. Here, we shall now describe some other properties of the electric charge. If the sizes of charged bodies are very small as compared to the distances between them, we treat them as point charges. All the charge content of the body is assumed to be concentrated at one point in space. 1.4.1 Additivity of charges. We have not as yet given a quantitative definition of a charge. We shall follow it up in the next section. We shall tentatively assume that this can be done and proceed. If a system contains 2-point charges Q1 and Q2, the total charge of the system is obtained simply by adding algebraically Q1 and Q2, i.e., charges add up like real numbers or they are scalars like the mass of a body. If a system contains n charges Q1, Q2, Q3, Qn, then the total charge of the system is Q1 plus Q2 plus Q3 plus Qn. Charge has magnitude but no direction, similar to mass. However, there is one difference between mass and charge. Mass of a body is always positive, whereas a charge can be either positive or negative. Proper signs have to be used while adding the charges in a system. For example, the total charge of a system containing 5 charges plus 1, plus 2, minus 3, plus 4 and minus 5, in some arbitrary unit, is plus 1, plus 2, plus minus 3, plus 4, plus minus 5, equals minus 1 in the same unit. 1.4.2 Charge is conserved. We have already hinted to the fact that when bodies are charged by rubbing, there is transfer of electrons from one body to the other. No new charges are either created or destroyed. A picture of particles of electric charge enables us to understand the idea of conservation of charge. When we rub two bodies, what one body gains in charge the other body loses. Within an isolated system consisting of many charged bodies, due to interactions among the bodies, charges may get redistributed, but it is found that the total charge of the isolated system is always conserved. Conservation of charge has been established experimentally. It is not possible to create or destroy net charge carried by any isolated system, although the charge-carrying particles may be created or destroyed. Figure 1.2 Electroscopes. A. The gold leaf electroscope. B. Schematics of a simple electroscope. Electric charges and fields. 5. In a process, sometimes nature creates charged particles. A neutron turns into a proton and an electron. The proton and electron thus created have equal and opposite charges, and the total charge is 0 before and after the creation. 1.4.3 Quantization of charge. Experimentally, it is established that all free charges are integral multiples of a basic unit of charge denoted by E. Thus charge Q on a body is always given by Q equals n, where n is any integer, positive or negative. This basic unit of charge is the charge that an electron or proton carries. By convention, the charge on an electron is taken to be negative, therefore charge on an electron is written as E and that on a proton as plus E. The fact that electric charge is always an integral multiple of E is termed as quantization of charge. There are a large number of situations in physics where certain physical quantities are quantized. The quantization of charge was first suggested by the experimental laws of electrolysis discovered by English experimentalist Faraday. It was experimentally demonstrated by Millikan in 1912. In the International System, SI, of units, a unit of charge is called a coulomb and is denoted by the symbol Ca. Coulomb is defined in terms the unit of the electric current which you are going to learn in a subsequent chapter. In terms of this definition, 1 coulomb is the charge flowing through a wire in 1s if the current is 1 ampere, see Chapter 1 of Class 11, Physics Textbook, Part 1. In this system, the value of the basic unit of charge is E equals 1.602192 times 10 to 19 C. Thus, there are about 6 times 1018 electrons in a charge of -1 C. In electrostatics, charges of this large magnitude are seldom encountered and hence we use smaller units. 1 millicoulomb, microcoulomb, equals 10 to 6 C or 1 millicoulomb, millicoulomb, equals 10 to 3 C. If the protons and electrons are the only basic charges in the universe, all the observable charges have to be integral multiples of E. Thus, if a body contains n1 electrons and n2 protons, the total amount of charge on the body is n2 times E plus n1 times E, equals n2 n1, E. Since n1 and n2 are integers, their difference is also an integer. Thus the charge on any body is always an integral multiple of E and can be increased or decreased also in steps of E. The step size E is, however, very small because at the macroscopic level, we deal with charges of a few mC. At this scale the fact that charge of a body can increase or decrease in units of E is not visible. In this respect, the grainy nature of the charge is lost and it appears to be continuous. This situation can be compared with the geometrical concepts of points and lines. A dotted line viewed from a distance appears continuous to us but is not continuous in reality, as many points very close to. 6. Physics. Example. 1.2. Example. 1.1 Each other normally give an impression of a 1.1 Each other normally give an impression of a continuous line. Many small charges taken together appear as a continuous charge distribution. At the macroscopic level, one deals with charges that are enormous compared to the magnitude of charge E. Since E equals 1.6 times 10 to 19 C, a charge of magnitude, say 1 millicoulomb, contains something like 1013 times the electronic charge. At this scale, the fact that charge can increase or decrease only in units of E is not very different from saying that charge can take continuous values. Thus, at the macroscopic level, the quantization of charge has no practical consequence and can be ignored. However, at the microscopic level, where the charges involved are of the order of a few tens or hundreds of E, i.e., they can be counted, they appear in discrete lumps and quantization of charge cannot be ignored. It is the magnitude of scale involved that is very important. Example 1.1 If 109